For the first step, I went to the OpenSky network website, went down to data, downloads, states, and I just picked one of these and downloaded the CSV file. I just put it on the desktop and extracted it again to get the CSV. Here's the CSV file from OpenSky containing all the data. It has ICO 24 tags identifying each aircraft, the time at which this data point was recorded, and then all of these columns here. The most important ones that I analyzed would be last position update and last contact. A short explanation of what I did. If we look at the CSV file here, we have all of these times, and I isolated it to one ICO tag. So we have all these data points at different times for, say, this aircraft. What I did was I took those times, which all of these are recorded at a 1 second interval. So we have your normal time, which I'll call index time. What I analyzed is the gaps between the times. So this would have a 1 second gap, this would have a 1 second gap. So as far as the index time goes, this isn't dependent on any position updates. This is always going to have 1 second between each data point. Last position update is the last time that a GPS update was recorded in the data stream. So if we had one of these at 3, 4, and 7, this would have been a 1 second position update. This would have taken 3 seconds. By analyzing the gap between these position updates, we can figure out where the data drops out. The way I did this is if we took time index and then position update, at time 0, we get a position update to update our GPS coordinates also at time 0. So it will say this column, the last position update was at a time. So that first one was at time 0. The next timestamp happens and we get another position update. Okay, so that's fine. And right here, this would be a dropout. So at time 2, we get a position update. So our last contact was at time 2. But then at time 3, we don't get one. So our last position update was still at time 2. So we've missed one here. And then when time 4 happens, we get another one on time. So that's all okay. And then another strange thing that can happen is at time 5, we can get 2 position updates, which I think is caused by the server sending multiple packets instead of just one. So this would be the opposite of a dropout. This would be a piece of duplicate data probably. And then the next scenario at time 6, we get another update. How does this help us analyze dropouts? Well, if we subtract the time since last contact from the time index, we can figure out how long it took the message to get there. For the first one, the last message was 1 second ago at time 0. So we just have a 1 second message delay. And the same for the second one, get another 1 second. And then for the third one, another second. Okay, but then when we get to 4, we ended up not getting a message at 3. So this message took 2 seconds, which means it's half as frequent as it should have been. We should have gotten 2 position updates since the last time. Alright, so then for time 5, the last one was at 4, so that's good. That's another 1 second. For this one, the double packet thing happens, which means that when we take this, the frequency of messages is instant because instead of getting one every second, it gets two in one instant. So this would set the delay to 0. I have created a plot of this versus time index. So if we have 600 data points and we want to go through each of those time indexes, which would just be the row number on Excel, we can look at the time since last contact over a period of time, which is what I've done in this chart. The longer the delay, the higher the amplitude of this spike is, the more time has elapsed since the last position update. So the higher the spike is, the longer the dropout is. So we had a big 3-second dropout here, and then it was fine again, receiving messages every second. And then we had a smaller dropout here for 2 seconds. And then we continue along and at a 1 second, so standard again. And then we get a dip here, which is where the server received 2 packets, I think. So that's just kind of the opposite. We got extra data, which doesn't really matter. It's probably duplicate anyway. And then the rest of the graph continues and has a couple dropouts. The second graph I made was to analyze this graph because I wanted to know what the distribution of time between messages was. For this graph, you can see that most of the messages had a 1 second delay, which is good. This would be our baseline. And if this line was a little more random or noisy, we could use this to tell what the intended message delay was. Also notice that this is a graduated scale because when you have 600 data points and most of them are 1 second since the last position update, it's really hard to see smaller values. So for this one, I mean there were 350 and most of them were 1 second, and there were only a couple that were 2 seconds since the last position update. So that's the reason this is graduated. Okay, so what can all of this be used for? How do we detect dropouts with it? Well, if we take a graph of an aircraft like this that goes along and then has spikes and has another spike and then a dip, what we really care about is detecting these spikes. And for different aircraft, the server response time may be different. So your baseline here could be 2 seconds, could be 1 second, could be 3, depending on the type of system. So what we need to do is we need to figure out that average, which is easy to see using this plot. And then we need to detect any data points that have a larger than average delay between them. So if the average delay is 1 second, anything up here in this region would be a dropout. And anything below this region would be normal or a duplicate packet like it is right here at this dip. What this tells us is dropout detection for different aircraft systems is going to be very subjective. When we have a baseline of 1 second, a 2 second dropout could cause major damage. But if you have a sensor that's hovering or something less critical, you only get a server response every 5 seconds. Let's say a 2 second dropout is actually just going to be duplicate data like it is down here. My plan for detecting them using this is pretty simple. We'll just find the baseline and then flag any message that takes longer than the baseline to arrive, and that'll be our dropouts.